Alright, second hour. Okay, so if you get rid of all the hash of zeros and so on, you can see that the read function isn't actually that long. Okay, so we read the first line, we scan the 2 digits of that, we create an image, and then we fill it up with the values that we read from the rest of the file. Alright, so that's that. Copying an image. One thing that this does, it actually takes in an existing image and creates a new image. So there's a lot less messing around with ampersands on the arguments and a lot less arguments. Certainly if you're copying the whole image, this one we're copying part of the image, so we've got to feed in the top left and bottom right values. But for copying the whole image, it's very simple. We simply return a copy that's based on the whole image. So starting from the top left and going to the bottom right. Oh, how annoying. Okay, and that's it for copying the whole image. We just make use of that function that we're about to write. Okay. Alright, so PBM copy takes an image and copies part of the image from the top left to the bottom right. Alright, so if we're going to do that, one thing that we need to do up front is to get a new height and a new width for the new image. And I guess I can declare all those variables. Alright, so what's the new height is basically, and remember that the top left is going to be smaller values and the top part is going to have smaller values than the bottom part, which I guess is something we could check as well with an assert. X has to be less than bottom right x, and top y has to be less than bottom right y. Otherwise we've got a nonsensical new image that we're creating. We've got the top left up here and the bottom right over here somewhere, which doesn't make sense. Okay, so if that's all true, then we can easily compute the new height as the bottom right y value minus the top left y value minus 1. Okay, otherwise we end up, is that right? Oh no, it's not minus 1. Is it right? Minus 1, not minus 1. Not minus 1. Good. So the count of the number of values, and the new width is bottom right x minus top left x. Right, so that gives us the size of our new image that we're going to make a copy into. We can then create the image. New is assigned PBM create. Now that we've hidden all of the difficult work in here, new height, new width. So that sets up a completely empty image, and then we can grab the relevant part, and it sets up a new image of the appropriate size, and then we can grab the appropriate part of the existing image and copy that across. Alright, so once again, row and col for row starting at the top left. And in this case, we have to go to the bottom right, because I guess the notion is that we include the top left coordinate and the bottom right coordinate. So I've got to keep doing it backwards because you're facing the other way. This is actually wrong. Why didn't you tell me? You said it wasn't -1. I get the feeling it's +1. Is that right? If the top left x, top left y is 2, we're starting at row 2, and we're going down to row 4. 4 minus 2 is 2, but we've actually got 3 rows there. So, and I realise that because of the for loop, until that goes through x plus 1 times. Right. And it's just a straight nested for loop. Equals, let me see, top left x. So it's handy to put the braces in before you put the contents of the braces. Alright, so, let me see, should I compute? Maybe I will. What will I call it? So that gives me the row and column values within the new image as opposed to the row and column values in the old image, which is what these are giving me. And then I should just be able to say new pixels. What's it called? Image. I hate that. Stick it like that. Okay? So mapping the old coordinates into coordinates in the new image. So I reckon that's pretty much done. Yes. So the PVM create has set the height and width of the new image, so that's fine. So I think all we've got to do at the end here is just return a new image. Okay, so that's a little ADT that might have made writing bits and pieces of assignment 1 a little bit simpler. Don't know, maybe you disagree, but I would argue packaging up some useful stuff that's related to a particular data structure in your program, packaging that up as an ADT is generally a good idea. Any questions? Any comments that I've stuffed something up before I leave that there and you go and have a look at it and I'm embarrassed? Nope. Okay. Alright. So write that out. That was there merely for explanation. Close that saving. Alright, let's go back to notes. Alright, so that was just my look at part of assignment 1. Of course, there's all the stuff where you've got to do the actual calculations and work out how many verticals there are, how many holes and all that, but they're a little bit separate to all of that. Alright, so we haven't talked about them. We talked about the debugger last time. So that's a useful tool for dealing with programs. Another useful tool for dealing with programs crops up particularly when programs start to get large. But if you're working as an individual like you were on assignment 1, for example, it's easy enough for you to maintain the code in your working directory. You know, you've got an AS1 directory that's got all the code for your assignment 1 stuff. You edit the files there, try to compile them up. If they compile up, you submit them or you run them through an auto tester. But basically just editing in place, you're making some changes, testing those changes presumably, and then you've got a new version of the code. That's all very nice, but what if you make some changes and you test it on the first 20 sample inputs and it works alright, and you say, okay, that's it, I'm done. And then you run it through the full test suite and it fails on all of the rest of the tests. Whereas before, it passed almost all of the rest of the tests. Damn, I've made these changes and I've screwed things up. What do? Well, if you're lucky, you kept an old copy of your code somewhere. If you're not lucky, and if you're just working in place, like I'm talking about here, then you'll have to go back and undo those changes that you just made. Right, which can be a little bit tedious, can be error prone, and so on. So even an individual maintaining code, it's occasionally useful to be able to back up what you did. So the fact that you're using Give and Give is going through GitLab is actually saving old versions of your code, and you can actually extract the old versions from there if you really mess things up badly. Another scenario where it's not just an individual now, it's a bunch of people. So if you're doing group projects, you might have the code sitting in a single directory and everyone's hammering away at the code. One issue, of course, is if you've got 2 people editing the same file at the same time, that's a problem. But even if they're not editing things at the same time, you might have one programmer who's adding something new to a program and someone else who's fixing a bug in the same program but at different times, and they happen to be working on separate copies. That's a serious problem, but here we're talking about a single code base. But at some point in time we need to make sure that all of the changes go into the prog.c file. This wasn't the original version of this that I had. In fact, the next step up is where the 2 programs are working completely independently. So you've got a copy of all the files for the assignment. Another program's got a copy of all the files for the assignment. Programmer X makes some changes to the file prog.c, to their copy of prog.c. Programmer Y makes changes to their copy of prog.c, and at some point those 2 files have got out of sync and we've got to bring them together and make sure that all of the appropriate changes have been incorporated. And there may be conflicts in what people have done. So one of your fixing a bug might affect the changes that added the new feature. So that's an even more complex scenario where we've got code distributed. So what we need for that, we generally need some kind of assistance in the form of a tool, and over the years there have been a whole lot of different revision control or source code control or whatever you want to call them, systems that have been developed. You know, there was an old thing called SCCS and then RCS and then CVS. Nowadays, pretty much everyone uses Git. So the deal is that we have a single repository that contains all the different versions of the code, and it stores them very efficiently, and at any point in time a programmer can go to that repository and extract version 5, and it'll get a complete copy with all the appropriate changes made for that version. So a programmer can grab a copy, do some work, and then push the changes back into the repository. Now, if you've got multiple people doing that, then when you try to push something back, it might recognise, hey, you got version 5, now you're trying to create version 6. Someone else got version 5 and they've already created version 6. What's the difference? What do we need to do to fix, to resolve that? So there's potentially a merge step where you have to put together bunches of changes. Now the system sometimes can do that automatically. If you make a change to one part of the code, someone else makes a change to another part of the code, and those two parts of the code are completely unrelated, then sure, you know, you can put this version of this function and this version of some other function and put them in a single file, and you're happy. Alright, so what Git does is it effectively implements something like that. And I've got a very rough diagram of what's going on with Git. So notionally there's a global repository which could be on GitHub. A lot of people already use GitHub. Could be on Bitbucket, and I'm sure there are other. Oh, it could be on GitLab, which is more of a local CSE Git repository. So somewhere stored away from your directories is a bunch of copies, or a copy of all the versions of a particular source code. If you wanted to get started initially working on a project and there was already some versions in the global repository, you could do a clone operation which would give you copies of all of the files. And presumably, I haven't checked, you can specify that you want a particular version, and it will give you a particular version of what's in the repository. So you can sit there and you can make changes to that file, get a modified version of that, and then what you do is, rather than pushing it directly to the global repository, what Git allows you to do, which is different to what all of the other previous systems did, was they allow you to maintain your own local repository as well as having the global repository. So if you make modifications, you don't directly put them into the local repository. You probably only want to do that once you've made, you know, a certain number of changes that justify making a new version of the system. But in the meantime, what you do, whenever you make some changes, you can say add, and the changes will be stored in what's called a staging area. Once you've decided, and you know, it's not just prog.c, there might be a whole bunch of other .c files, .h files that you're fiddling around with. Once you've decided that you've made enough changes to a bunch of files that you've generated what you could call a new version, you can then commit that version. So all of the updated files will be popped into your local repository, and you can sort of keep cycling through that process for a while. Once you've decided that, all right, this is serious enough that a new version has to be pushed onto the global repository, then there's an operation called push that will take the current copy from the local repository, or probably one that you specify, and send that back to the global repository. So at each of these steps we can have, not at each of these steps, when you try to do a commit, there's a potential problem, there's a clash with something that's already in the local repository. Similarly, when you do a push, there's potential for a clash as well, and those clashes have to be resolved manually, in general. So Git is quite a useful system. It allows you to get a working copy of your code sort of local to you. So all this black stuff is meant to be on your local machine, and there's a global copy of the system into which you can deposit your new versions of the system. How's that all controlled? Well, there may be someone who's in charge of the global repository, and they're responsible for reconciling pushed changes. Right, anyway, you don't have to worry about this at this point because Give is doing all of the work for you. It's pushing stuff into the local GitLab repository that we've got inside CSC. But in future, when you start working on projects and you've got multiple people involved working on the project, definitely have to get into using a version control system. So they're going to talk about that in COMP1511. Alright, another tool that I've talked about before was Make. So once you've got a bunch of files there, it's a little bit difficult sometimes to keep track of what's changed, what needs to be recompiled, and what files depend on what other files. And basically the dependencies are like, if you want to recreate this binary, you need to get this set of object files need to be linked together to create the new binary. And also another kind of dependency is if you've got source code files that hash include other source code files, include .h files. If you change the .h files, then potentially you're changing what happens in the compiled version of the .c file, so you'd have to go back and recompile. So once you've got enough files, if you've got 6 files like you had with assignment 1, or 6 or 7 or 8 or anything less than 10, it's not really a problem to keep track of what depends on what. But if you've got a larger system, then it's potentially difficult to keep track of what's happening. So if you made a bunch of changes, before you commit them, you want to test them out, then I've changed a bunch of source codes, I need to produce a new executable. What do I need to recompile? Well, you've got to remember, alright, I changed this .c file, I need to recompile that. Change this .c file, I need to recompile that. Change this .h file, and that's used by another bunch of .c files, so they will all need to be recompiled. So one way of handling it is just to say, I give up, I'll just recompile everything. Now that's okay if you've only got 8 files, but once you've got several hundred files in a large project, that's not really a smart way to do things, or certainly not an efficient way to do things. So the other thing is you can try to keep track in your head what you've changed and what depends on what you've changed, and therefore what needs to be recompiled. But if you don't want to keep track in your head, we have another solution, Make, and Makefiles. So Makefiles essentially allow you to document dependencies. So you can say this file here depends on this file here. So if I ever change this, I'll need to change that in some way. And they allow you to document dependencies, but they also allow you to document how you go from this version of the file to this other, not this other version of the file, but say from a .c file to a .o file. Okay, so what commands are required to go from this source here to this target? And Make it smart enough to understand, to look at all these dependencies and say, alright, this has been changed, therefore I need to change this. And then there's a rule that tells you how to change it. So the way it works all that out, it looks at the file update times and it says I've got a target here, .o file. The .c file that was used to create that is newer than that, therefore I need to do a C compile on the .c to produce a new version of the .o. So let's just take a look at an example makefile, which is kind of typical of a very small makefile. This comes from the examples last week with Q. Okay, so a couple of things that you can do in a make file. There are a number of variables that allow you to control how the various rules are done. And so you can specify what C compiler I want to use if I don't explicitly mention the C compiler. You can write, I've made this fairly compact by not specifying a lot of the rules. Make is able to infer rules for various kinds of transformations. But here we've been a little bit explicit, so I've defined, if you like, the variable cc to be equal to dcc. So if I write $cc, that basically says replace this by whatever the value of cc is, so that'll put dcc there. What this whole thing is, it's basically, here's a list of dependencies. If I want to make Q1, then that depends on Q.O and QArray.O. And how I generate Q1 from Q.O and QArray.O is by executing this command here. So I do a C compile which links those two .O files together and puts the output into the Q1 program. Now, like I said, if I really wanted to, I could have written that as DCC. But, of course, if I decide to change the C compiler and I've got DCC all through the code, then I'd have to go through and change all the DCCs to whatever, say I want to use GCC or something. The other thing that you can do, there are various special built-in variables that get used. C flags is one of them. It allows you to specify flags to the C compiler. So I'll put this back to what it was. Alright, and let's just take a look. So at the moment I've got Q.C, I don't have a Q.O, I've got QArray.C, no QArray.O, no QList.O. So if I run make, using that make file, then it understands that to get Q.O, I need to compile Q.C, and it compiles it using that particular C compiler with that particular flag. That's one I've specified. It understands that these flags here are also required. And if I want to make the QArray.O file, then I need to compile QArray.C. And then to make Q1, which is what triggered this whole process, I need to link those two files together and put the output in Q1. Same deal for QList to make Q2. So notice that here it doesn't recompile Q.C because it knows that now Q.O is up to date. So it just recompiles Q_list and then links the new Q.O to QList.O. And like I said, it's smart enough to understand that when things are up to date, you don't need to recompile anything. If I were to say change QArray.C, so that's not doing anything with the file, it's just making it look like it's been changed. And then I do make again. Now it sees QArray.C has been changed, therefore I need to make a new version of QArray.O because QArray.O is required by one of the executables that I'm trying to make. So if we go back to the make file, right, so when I type make, what make tries to do, it looks for the first set of dependencies in the file and it tries to make all of this, or tries to make what's mentioned there. Now, another thing that make allows you to do is to specify dependencies but not have an associated rule. So when I type plain make, it tries to make all, which basically means I want to make Q1 and I want to make Q2. So that's all that dependency up there is saying. So it's just a way of bundling those two things together. If I didn't have that, if I turn that into a comment, and let's save, and I go back here, and I do a make clean, and then I do another make, it should only make Q1. Why does it only make Q1? Because it looks through the file and it tries to make the first target that it finds. Okay, so Q1 was the first target. But if this is the first target, it says, all right, in order to make all, I need to make Q1 and I need to make Q2. So now that they're both there, if I type make again, it'll say Q1 is up to date, or it'll know that Q1 is up to date, but it will also know that it needs to recreate Q2 because I asked for that. Alright, so what make says, alright, I need to make Q1. What do I need in order to make Q1? Well, I need Q.O and I need QArray.O. How do I get Q.O? And it looks for a rule where Q.O is the target. And it sees this one here and it says, okay, Q.O depends on Q.C and it depends on Q.H. Because if we go and look in Q.C, it's got a hash included with Q.H. So if I was to go and change Q.H, I'd need to recompile Q.C, even if I hadn't changed the code for Q.C. So, in order to make Q1, I need to make sure this file exists and is up to date. So how do I do that? I look for a rule with Q.O on the left-hand side, and then I look at the sources that produce Q.O, and I check, is Q.C newer than Q.O? And if it is, it means I've made a change to Q.C, therefore I need to recompile. Is Q.H newer than Q.O? Well, if that's the case, I need to recompile. Now you may notice here, all I've got is dependencies. I don't actually have a command that specifies how to create them, but make understands enough about .c and .o to know that if you've got a .o that depends on the .c, then you need to do cc minus c. If I really wanted to, I could be explicit about it. And say, do this. .c. So I could do that if I want. But like I said, it's smart enough to know. In fact, if you're watching carefully, you may have noticed that it actually uses that notation as well when it's converting a .c file into a .o file. That's not strictly necessary. So if I was to touch, let's touch Q.H. And now it knows that it has to remake everything. It actually added that all by. Oh, I know what happened. I didn't save. Didn't save the new version. So let's touch Q.H again. Run make. Alright. You can make syntax errors in make files. What's wrong there? You won't see a problem with that line? I can't. I hope that's not converting. I have a bad feeling it might be converting that into spaces. It has to be a tab. Alright, let's abandon gedit. Use a proper editor. say tab? Oh, I want tab. Right. So you may notice this time it's actually using a rule that I wrote explicitly, which doesn't mention minus O, Q dot O. But a derived rule will always do it that way. So make's being helpful. It's saying, well, I understand how to make a dot O from a dot C, you don't need to tell me, so I can leave that stuff out. Other things you can do with the make file, you can have targets that don't have any sources involved with them. And basically if I say make clean, it's always going to execute the rule. So make clean basically says remove all that stuff. And the reason I'm using -F is if I type make clean and those files don't exist, then the rm command yells at me, complains that the files that I'm trying to remove don't exist. Okay. So it's important things about make files. You can document dependencies between files. So basically what this rule here is telling me is if I change either of q.c or q.h, I need to recreate q.o. And the same, if I change q_array.c or q.h, I need to remake q_array.o, and so on. Any questions on that? Extremely useful. So once you set up a make file, the make file just sits there and you edit away, You want to rebuild the system, you just type make, and it knows exactly what needs to be recompiled. Very convenient. Of course, if you're using an IDE of some sort, Eclipse maybe, it's probably got a rebuild functionality that does similar kind of things. That makes everything explicit. And there's much more complicated make files than this, especially if you've got a project that's got multiple levels of directories. You've got a database system with the indexing schemes in one directory and the query evaluator in another directory and so on. You run the top level make file and it triggers make files in the lower level directories, and it can go down as many levels as you like until you've rebuilt the entire system. Alright, if there's no questions, then we can finish early and come back for one last look at what's on the exam. Maybe a special guest lecturer. So I'll see you on Wednesday at 11.